I said yesterday there was two important measures we like to look at, and yesterday we saw about expected value or expectation. Today we'll look at the other one, variance. Again, we talk about discrete random variables. The variance of our random variable is found via this formula. The sum of x minus mu squared times the probability of x. Mu, as we saw, has the same value as the expected value of x. Now this thing, x minus mu, that we're interested in is what's called the deviation. How far away is it from the average, basically? That's what we're talking about. Thus, it's a measure of spread. That's what it is. How far away, how spread out is the information. Let's go back to our survey from yesterday and work out the variance. And remember, yesterday we came up with this table. So that's the point we got it to. Remember, mu was 2.2. So that other row now, I'm interested in x minus mu squared. So I'm now going to take away x minus mu, 2.2, and square it. And there's the values that we come up with. Now I haven't bothered summing that row because that's not the sum I want. I want the sum of that times px. So now I'll add in another row and multiply all of that times the probability of x, and it's that sum I'm interested in. So that's 1.52. So there is our variance, 1.52. Now personally I find that a very laborious process. There's another way we could do it if we play around with it a bit. So remember, we said this is variance. But if you look at it, it's in the same form of expected value. But it's not the expected value of x, it's the expected value of x minus mu squared. Because we've got x minus mu squared and we've multiplied it by the probability, and that's what we were doing with expected value. But now if I play around and say, well, hang on, if I expand out x minus mu squared, I get x squared minus 2 mu x plus u squared. But I've got these three things that are sums. Okay, one of them is negative, so I could break that up. But also, I can factorise out the constants. So in the second one, I've got 2 mu times the expected value of x. The last one, the expected value of mu squared. Well, mu squared is a constant. The expected value of a constant must be that constant. It's going to be that every time. That's what I expect. So I now have the expected value of x squared, but hang on, expected value of x, that's mu. So that now becomes expected value of x squared minus mu squared, where expected value of x squared will now just be x squared times px. Why is that easier? Because now look what I can do with the table. I've got the probability of x. I've already found xpx when I did expected value of x. And there it is over there, 2.2. But now I just go, right, I'm just going to multiply this by x. So I just create a third row. And look, to me that's just a logical structure. It goes px, xpx, x squared px. A very logical structure. And 6.36 then is the expected value of x squared. So to work out the variance, I'll go, well, that's the expected value of x squared minus the expected value of x squared. Okay, I've written it as mu, but in my head it's easier to think of it that way. Expected value of x squared minus expected value of x squared. And there it is, 1.52. I think that's a neater solution. I think a much more logical process to do it through. Well, that brings up this thing called standard deviation. The random variable x is measured in some units, whatever it is we're measuring. Well, that means our variance, because we've found the expected value of x squared, and we've taken away the expected value of x squared, then its units must be units squared. Now, if I want to measure the spread, I want it in the same units. And that's why we have standard deviation. Because all standard deviation is the square root of the variance. And then that brings the units squared back to units. And then we've got them in the same units, and comparison becomes nice. And that's why we have standard deviation. So the standard deviation is the square root of the variance, or a nicer way of saying it is. And you might even see this symbol used for variance. The sigma squared is equal to the variance of x. So in our one, the standard deviation would be the square root of 1.52, which is 1.23. And that tells us a bit more about the spread. That brings up another idea, standardising data. How do we standardise it to make comparison? I want to compare one set of data to another set of data. Now, the original data has a particular average or expected value and a particular standard deviation or variance being the deviation squared. So I'm going to create a new random variable, which I'm going to say is my old one, just plus some constant number. I'm going to add a certain amount to every result. So now I want to find the expected value of this new random variable. But I can use my different rules and say, well, that's going to be the same as the expected value of x plus the expected value of this constant. Well, expected value of a constant is c. The expected value of x would be the mean. And you can see all we've really done is we've just moved the average up. Well, that makes sense. If I added a certain amount to everyone, then the average would go up by that same amount. But what happens to the spread of the data? So I'm now looking at the variance of x plus c. Well, that would be the expected value of x plus c squared minus the expected value of x, in this case, the expected value of y squared. I can expand out my mu plus c squared, and then on the left-hand side, I'll play around with those expected values, and playing around with it, I end up with the expected value of x squared minus, hang on, I've done nothing to the spread at all. I've ended up with the same thing. It's still the variance of x. Because what we've really done is this. Here was the original set of data, and we just added something. So all we really did was shift the curve. The actual shape of the data hasn't changed. So yeah, the spread stayed the same. Now the disadvantage with doing that, I mean, it sounds lovely and it makes people feel better because they've all got an extra, 5 marks, 10 marks, whatever. But imagine if you had a situation like this where, sure, you've got this low average and people want the average to go up, but someone's sitting there on, say, 97. Now, there might be an outlier. Now they're at 97. I'm going to add 5 to everyone. So you get 102. Oh, hang on, I can't do that. So not necessarily a great way of doing it, depending on what the data is. So another idea is, well, what we'll do is we'll divide it by a certain amount. And if I want the average to go down, I'll divide it by a number that's bigger than 1. If I want the average to go up, I'll divide it by a number less than 1. And then that should do that. So I'll get every piece of data. Well, what happened? So I've got this new random variable, which I'm going to call z. Expected value. Well, the constant on the bottom, I could factorise that out. And so it's expected value of x over k, and sure enough, the average would be divided by that constant amount. Makes sense. Variance then. Let's play around with that one. Again, I could pull out the constant, well in this case constant squared, it'll go on the bottom. So on the top I've got the expected value of x squared minus mu squared. Oh, hang on, that's the variance of x. So I've also divided the deviation, or the standard deviation, by that same constant. What does that do to the shape of the data? So what we've said is, here it is. In this example, I'm saying I'm dividing by a number bigger than 1, so the average would go down. But also, the spread's tightened in, because I'm dividing that as well. So it's become a smaller spread, so that the data becomes tighter. So it'll do something like that. Now, in reality, what's the great way of doing it is our z-scores. It sort of combines the two ideas. What we call normalise the data. And there's our formula. This is what we do. We actually do shift the curve. So we've got x minus the average. But then we also divide it by the current, whatever the current deviation is. Now, why do it like that? Because look what happens. The expected value of z would be x minus mu over sigma. Okay. Well, that's a constant, so I can say it's the expected value of x minus mu over that constant. Expected value of x is mu, and expected value of mu, well, that's a constant number, so it would be mu. Bang! It gets the average to 0 every time. What happens to our variance? Okay, same idea. Well, I could factorise out the sigma squared, and then on top we get the variance of x minus mu, and that will turn out to be sigma squared as well. It turns out to be 1. And that's beautiful, because what that's saying is it's that one deviation from the mean. And that's why it's such a beautiful way of looking at data. It's symmetric around 0. Some have to be negative, some have to be positive because of how we shape the data. Negative doesn't mean bad, it just means below average. 13C then is playing with variance.